Okay, shout out to JGL today. It's obviously Optional Monday. And we will miss you. Who knows what that looks like? That is a problem. How about this one? Yeah? How about this one? So today's question is, what about that? Okay, we got somebody who already knows. Campbell knows exactly what this shape looks like. Do you know what this shape looks like? So we're going to help everybody discover those by simply plugging in some points or figuring it out. So it's this graph of following exponential functions. So our last few days that we're going to spend together, we're going to look at exponential functions and logarithmic functions. And we're going to look at the very basics. We're going to try to make it as straightforward and simple as possible. We're not going to get too complicated. But this is what we have. We make an X, Y, T chart. And we're going to plug in -3, -2, -1, 0, 1, 2, and 3. And so this is going to model your assignment today. You're going to try to graph exponential functions by plugging in points. You want to eventually notice some patterns develop. I'm going to start at the bottom. I'm going to plug in 3. When I plug in 3, you get what? 27. 3 to the third is 27. Then I'm going to plug in 2, and I get 3 squared, which is 9. Then I plug in 1, I get 3 to the 1 is 3. Then I plug in 0. Does anybody know what something to the 0 power is? Do you know why? Would you agree that if you take two things that have the same base and divide, you subtract the exponents? Everybody agree this is x to the 0? And if you take something divided by itself, you get 1. That's why something to the 0 is 1. So you're right. If I plug in 0, I get 1. Now, let's get a little bit trickier. I have 3 to the -1. How do I do 3 to the -1? 1 over 3. So what about 3 to the -2? Very good. 1 over 9. And 3 to the -3? 3 to -3? 1 over 27. So I'm going to make a little chart here. 10, 20, 30. 1, 2, 3, 4. 1, 2, 3, 4. And this is part of the pattern that you want to notice. Look at these y values. I have -3 and 1/27. 1/27 is a really small value, isn't it? So I'm going to plot it right here. 1/9 is also a really small value. I'll plot it just right above the x-axis. 1/3 is also a really small value. I'll plot it right above the x-axis. 0, 1, that is going to be just a little bit above the x-axis. As you notice, it starts to get a little bit taller. 1, 3. 2, 9. 3, 27. So if you notice, the graph will never go below what? It'll never go below 0. It'll never go below the x-axis. But as you can tell, as you go to the right, it gets bigger much more quickly, doesn't it? And we call it exponential, and it models growth in this world. In fact, I'm going to use it to teach you a new number, a number you've never seen before. This will be kind of neat. We'll try this one, and then you'll do a couple of problems on your assignment, and then we'll go back to it. We got x and we got y. What's different about this one? Yep, we got a negative. Now, let's see what happens. If you plug in -3, you end up with 4 to what power? 4 to the third, which is 4 times 4 is 16, times 4 more is 64. If I plug in negative 2, what do you get? 4 to the, which is 16. Plug in negative 1, you get 4 to the, which is, plug in 0, you get 4 to the 0, which is 1. Plug in 1, you get 4 to the negative 1. What is 4 to the negative 1? 1/4. Plug in 2, and you get, yeah, somebody said it's flipped. Who said it's flipped? Very good. It is flipped, and we get 1 over 64. Watch what happens when we plot these. I'm going to, make 20, 40, 60, 80. 20, 40, 60. We got 1, 2, 3, 4. 1, 2, 3, 4. And as you plot these, I have a negative 3 and a positive 64. Negative 2 and a positive 16. Negative 1 and a positive 4. Again, I'm approximating these values. 0, 1. 1 and 1/4. 2 and 1/16. 3 and 1/64. As you notice, the values get increasingly small. And it just kind of levels out along the x-axis right after that. So what I want you to do is, I'm going to pause the video. I want you to do the first 2 problems on your worksheet. Make a table of values, x and y, use negative 3 to positive 3, and make the shapes. Go ahead. All right, what's different about this one? A little bit of everything? Not really. Let's try being more specific. What's different about this one? You have a fraction. Let's consider what happens with a fraction. Let's not make it too difficult. Let's make it nice and easy. And I'm going to start by plugging in the negative 3. I get 1/5 to the negative 3 power. What do you do when you get something to a negative power? Yeah, you put it where it's not. You flip it. So this ends up being 5 to the 3rd. What's 5 to the 3rd? 125. So the next one will be 1/5 to the negative 2. 1/5 to the negative 2 is the same as 5 squared, or 25. And then I have 1/5 to the negative 1. 1/5 to the negative 1 is the same as 5 to the 1, which is, anything to the 0 is 1. 1/5 to the 1, 1/5. 1/5 to the 2nd. What's 1/5 times 1/5? 1/25. And then 1/5 to the 3rd power will give me. So is this going to look more like the first graph or more like the second graph? Second graph, yeah. 50, 100, 150. Mark off 1, 2, 3, 4. 1, 2, 3, 4. And I plot negative 3, 125. Negative 2, 25. Negative 1, 5. 0, 1. And then you can see, I mean, after that, it doesn't really matter. The values all just get really close to 0, don't they? One more, then we're going to jump onto the back side of this for some notes. It won't be part of your assignment, but we're going to show you a problem involves some money. And I saw some people doing the simulator. Anybody taking personal finance right now? Small business? Okay. Well, we'll show you a good example of how you can apply some of this stuff to real life. So we have x, y. I'm going to type in negative 3, negative 2, negative 1, 0, 1, 2, 3. Everybody agree that this is the one that looks significantly different than the others? This one, without a doubt, the first couple examples we do with it, you might be a little bit confused, but trust me, It'll come to it. You'll gain a deeper understanding of how these work. Okay. I plug in -3. What's -3 minus 1? -4. So I get 10 to the -4th plus 2. What is 10 to the -4th? What's 10 to the 4th? 10 times 10 is times 10 times 10, 10,000. So 10 to the 4th is 10,000. Then it's 1/10,000th. So the negative power would be 1/10,000th, correct? So we have 2 and 1/10,000th. Now, notice in your other examples, the small results were all really close to 0, weren't they? This isn't really close to 0. It's really close to what? 2. Yeah, it's really close to 2. It's all right. Let's try -2. -2 minus 1 is -3. What's 10 to the -3rd? A 1,000th. So we get 2 and 1/1000th, which is really close to what? 2, right? Now I plug in -1. -1 minus 1, -2. 10 to the -2. 1/100th. So I get 2 and 100th. I plug in 0. 0 minus 1, 10 to the -1. A 10th plus 2 is 2 and a 10th. See how these are all really close to what number? 2. Yeah, because you're adding 2. It shifted it up 2 units. I plug in 1. I get 10 to the 0, which is 1 plus 2, 3. I plug in 2. 2 minus 1, 1. 10 to the 1 is 10, plus 2 is 12. And now I plug in 3. 3 minus 1, 2. 10 to the 2, 100, plus 2 is 102. So I'm not going to spend a lot of time in this graph, but what I am going to notice is you have values very close to what? Very close to 2. So I'm going to move a tick mark up 2, and we have this imaginary line here that it gets really close to. And it passes through a value of 1, 3. So over 1 and up 3. It goes right through there. And this is kind of the general shape of the graph. Hi. Here's part of what we learned. If you have b greater than 1, say y is equal to 5 to the x, it has a shape that looks like this. And it passes through the point 0, 1. And it has this imaginary line that it never crosses. It's called a horizontal asymptote. Do you remember what happened if it was y equals 5 to the -x, or if it was y is equal to 1/5 x? Remember how it looked different? How did it look different? What did it do? Instead of starting down and finishing up it, yeah, it went like that. So why are exponential functions important? Because they're the primary way in which debt and savings works. So we're going to give Gavin a gift. Gavin, we would like to give you $2,000. Are you okay with that? We're also going to invest it at an interest rate of 9%. And it's going to be compounded once a year. Gavin, key question, how long would you like to have it sit before you take it out and start spending it? He's going 90 days. So in other words, 1/4 of a year. So let's see how his money works for him at this time. We're going to figure this out. We're going to do 2,000 times 1.09 raised to the 0.25 power. And if he does that, he'll end up with an extra 43 bucks. Now, let's suppose we gave that money to Sierra. Sierra, how long would you like to let it sit before you start to spend it? How many years? She's going to let it sit for 50 years. Now, that would put you at what age? 60, well, 67, 68. So she's ready to work towards retirement. Let's see what happens. She lets it sit. She made an investment of $2,000. She didn't touch it after that. She didn't do anything. 50 years later, what does she have? She has $148,715. This is the beautiful thing of compound interest and making money over a long period of time. So one of the great things you can do when you graduate from college, I'm going to tell you how to be financially stable. Number one, you graduate from college or high school, you don't buy a $50,000 car right away. You buy a $5,000 car. And then you pay off whatever debt you have. Second thing, you start investing towards a retirement option right away. Because every year really matters. Look what happens if I take that same entry and instead of 50, I just change it to 45. What happens? All of a sudden, $96,000. Just 5 years off the end of that, and it changed dramatically, didn't it? You invest early on. Now, here's the deal. That interest gets compounded once a year. But there's other things in this world that don't get compounded once a year. For example, this is my friend Campbell's phone. Anybody else got a phone? You do know that your phone, generally speaking, has more bacteria than that of a toilet seat, right? Do you think bacteria wait for once a year before they multiply? They multiply continuously. And because they multiply continuously, here's what we get. I want to show you this last piece. It's a number that you've never seen before, but watch it. I go into y equals, and I'm going to type in this function, 1 plus 1 divided by x. And I'm going to raise that to the x power. And I'm going to say, suppose that we have that amount, and we multiply once a year. You multiply once a year, your base value becomes 2. How about bacteria multiply every 5 times a year? We get 2.48. How about they do it every 10 times a year? 2.59. What's happening to the number? It's going up. But watch what's interesting. Let's suppose the bacteria multiply 100 times a year. Not that much though, did it? Let's say it goes up by let's say that it multiplies 1,000 times a year. Let's say that it does 1,000,000,000 times a year. It actually levels off. It levels off at a very specific value. In fact, 1 plus 1 over infinity raised to the infinity power is a very special number. It's called E. 2.7183. And it's the base that we use for exponential functions in real life. E is a very important number. Kind of like pi. Pi is what? Very good. Very good. Okay. So just like pi is very important in geometry, E is extremely important in algebra and especially exponential studies. Good job. We have the other 2 problems you do on your assignment. You are done for the day.